Hello, everyone. Welcome to the TCS at Jagiellonian seminar. Today we have Andrew Suk, who is an associate professor at the University of California at San Diego. Andrew is well known for his work and beautiful results in discrete geometry, Ramsey theory, extremal combinatorics, and some other fields. Just to mention two papers, one that he's probably most famous for is the asymptotic solution to the Erdős-Szekeres problem on convex on the set of points in convex position in the plane, and another one which highly influenced my work is chi-boundedness of intersection graphs of grounded monotone curves. Okay, so we are happy to have you here, and Andrew will tell us about unavoidable patterns in complete simple topological graphs.
Okay, so thank you for inviting me to speak in this seminar. So I'll be talking about graph drawing, several problems I've been thinking about in graph drawing recently. I guess today, graphs that are drawn in the plane, they're frequently called topological graphs. And so just to be clear, a topological graph is just a graph where your vertices are points in the plane, and then your edges are curves that are connecting the corresponding points. And at least for me, I got into graph drawing through this famous or pretty well-known conjecture about quasi-planar graphs. So we all know by Euler's famous theorem that if you have an n-vertex topological graph with no two crossing edges, then the number of edges is at most 3n minus 6. And so in particular, if your graph is planar, the number of edges is at most linear in the number of vertices. And then we say that a topological graph is k quasi-planar if there are no k pairwise crossing edges. And so when k is fixed, for example, when k is, let's say, 3 or 4, there's this pretty well-known conjecture that states that every n-vertex k quasi-planar graph has at most big O of n number of edges. So in particular, the number of edges is still at most linear in the number of vertices when even for k quasi-planar graphs. This conjecture in general is still open. It was proved to be true when k equals 3 by Pak, Radojcic, and Toth, and also a bit later by Ackermann and Tardosh. It was proved earlier by Argwov, Arnov, Pak, Polak, and Sharir in '97, but they had this extra condition on how you have to draw your topological graph. So in particular, they had this simple condition, which I'll talk about in a minute. The case when k equals 4 was solved by Ackermann in 2009, but for k at least 5, this conjecture is still open. And I believe as of today, the best known upper bound for when k is at least 5 is this quantity here, due to Fox, Pak, and myself. And so in particular, when k is fixed, the best upper bound is essentially n polylog n. Okay, and so since this conjecture has been open for quite some time, there's been several variations of this conjecture. So I'll just highlight some of them here. So for example, if you insist that the edges are drawn with straight line segments, then Valtar showed that every such k quasi-planar graph has at most n log n number of edges, where k is fixed. This was later generalized to x monotone curves by Fox, Pak, and myself. And kind of generalizing it in a different direction, Rock and Wolczak showed that if you insist, or if you have this condition that any two edges intersect at most t times, where t is a fixed constant, then the number of edges is going to be at most, again, n log n. And this result, so it's not so hard to see in general that this conjecture here is closely related to understanding intersection graphs of curves in the plane. And in particular, coloring intersection graphs of curves in the plane with bounded chromatic number. So I won't go into this area of research, but since I'm giving a talk in the seminar here, I thought I would at least mention some of these very nice results that's clearly very closely related to this conjecture here. And actually what I'll be kind of focusing on in this talk is what happens in the dense setting when you have a lot of edges. Actually, I'll be focusing on the complete topological graph. So if you go back to this slide here, so this result here, one corollary you get from this, just by setting this equal to n squared, is that every complete n vertex topological graph contains n to the epsilon pairwise crossing edges. So in particular, no matter how you draw the complete graph in the plane, you're guaranteed to have this unavoidable configuration, which is this matching of pairwise crossing edges. And so more recently, what me and my student have been thinking about is what other large patterns can we find in complete topological graphs? It turned out that we were interested in finding large planar configurations. So I guess in this direction, the simplest question would be, can you find a large set of pairwise disjoint edges in the complete topological graph? If you think about this problem just for a little bit, you'll quickly realize that you're going to have to add some kind of condition on how you draw your topological graph, because it's quite easy to construct an n vertex complete topological graph with no two disjoint edges. So there's many things you can do. For example, you can just place your vertices down here, pick any point in the plane, and then draw all your curves through that point. And this complete topological graph won't have any two disjoint edges. And so in particular, you cannot guarantee to find large planar configurations in topological graphs in general. And so therefore, in order to kind of get around this situation, we'll add this what's called simple condition. So a simple topological graph is a topological graph where now you insist that every pair of edges have at most one point in common. And so for the rest of my talk, since I'm interested in these planar configurations, or at least configurations with large planar components, I'll only be focusing on simple topological graphs. And so therefore, in simple topological graphs, every pair of edges looks like one of these three pictures here. So either two edges have a common endpoint, in which case this would be the only point that they have in common, or they have a common interior point, in which case we say that they're crossing, or they will just be disjoint, like in this picture here. Okay, so it is known that if you take the complete n-vertex simple topological graph, it is known that you can find a large set of pairwise disjoint edges inside of there. So this was shown by myself and also by Fulik and Ruiz Vargas. So in particular, we showed that you can find n to the 1/3 pairwise disjoint edges in the complete n-vertex simple topological graph. This result was later improved by Ruiz Vargas to something close to square root of n. And then very recently, I was informed that Eichholzer and company improved this bound to constant times square root of n. Kind of interestingly, the proofs of these results here, they don't generalize to dense simple topological graphs. So the fact that it was complete was kind of essential in all of the arguments. And for dense simple topological graphs, if you want to find a bunch of pairwise disjoint edges, the best known bound is only roughly log n. And in order for me to kind of, I guess, describe this result, I need to go back to the sparse setting. And this actually goes back to this kind of famous conjecture due to Conway, which is known as the Conway-Thraco conjecture. So Conway conjectured that every n-vertex simple topological graph with no two disjoint edges has at most n edges. So basically every pair of edges either have a common endpoint or they're crossing. And he called these topological graphs Thracals. And so a linear upper bound is known on the number of edges in a Thracal, but this conjecture, whether it's 1 times n, is still open. And I believe as of today, the best known upper bound for this Thracal conjecture is due to Fulick and Pak, who showed this 1.39 times n upper bound on the number of edges. But I guess either way, we know that the number of edges in a Thracal is at most linear in the number of vertices. And then you can play the same game as before. Can you generalize? So if you have a simple topological graph with no k pairwise disjoint edges, is it true that the number of edges is at most linear in the number of vertices? And that's still open, even for k equals to 3. And as of today, the best known upper bound is due to Pak and Toth from 2003, who showed that if you do have an n-vertex simple topological graph with no k pairwise disjoint edges, then the maximum number of edges is at most this quantity here. And so finally, now if you ask that dense question, what if your graph is dense? Not necessarily complete, but if you have a dense simple topological graph, well, now if you just set this equal to n squared or epsilon n squared, then this is how you can conclude that dense n-vertex simple topological graphs have basically log n pairwise disjoint edges. And whether or not you can prove this log to polynomial in n is still an open problem. Okay, so what other large patterns can you find in the complete simple topological graph? Basically, the patterns that I've just described are just simply matchings. They happen to be either pairwise crossing or pairwise disjoint. But of course, you know, if you have some kind of favorite graph drawing, you can ask the same question of whether or not you can find that favorite graph drawing of yours inside every sufficiently large complete simple topological graph. But in order to make this question a little bit more precise, I'll need one more definition. So we say that two topological graphs G and H are weakly isomorphic if there's an incidence preserving bijection between G and H, such that two edges in G cross exactly when the corresponding edges in H cross. So they're not exactly the exact same drawing of a graph, but you know, their crossing patterns are exactly the same. So now with this notion of weak isomorphism, in sufficiently large, complete, simple topological graphs, what can you find inside of here? And at least for me, probably the simplest graph drawing one can think of, or maybe one of the most natural, is the complete convex graph, or the complete convex geometric graph, which I'll simply denote with this C sub m here. So this is just simply the complete graph drawn in the plane where the vertices are in convex position and the edges are drawn with straight line segments. It's pretty pleasing to look at, I guess. You can immediately tell which edges cross and which edges don't. It also has a nice combinatorial description, which is that you can order the vertices V1 through Vm such that two edges, let's say Vi, Vj, and Vk, Vl, these two edges cross exactly when the interval Ij and Kl intersect but are not nested. So in other words, when I is less than K is less than J is less than L, or when K is less than I is less than L is less than J. I guess in this picture here, it looks like I highlighted 1, 3, and 2, 4, which is clearly crossing. Okay, so I don't know, given that this is a pretty natural type of graph drawn in the plane, then you can ask, does every sufficiently large, complete, simple topological graph contain this thing here as a topological subgraph up to weak isomorphism? And kind of interestingly, the answer is no. This is not necessarily true. And the reason why it's no is because of the complete twisted graph, which I'll denote with this T sub m here. It's basically the complete graph drawn in this twisted way, like this. I would say that this is probably not so pleasing to look at. It's not immediately clear which edges cross and which edges don't. But actually, this thing here does have a nice combinatorial description, which is that you can order the vertices V1 through Vm such that in the complete twisted graph, two edges Vi, Vj, and Vk, Vl, these two edges will cross exactly when the intervals Ij and Kl are nested. So in other words, when I is less than K is less than L is less than J, or when K is less than I is less than J is less than L. So it's a little hard to see because you have these curves twisting around. But if you focus on the edge, let's say 3, 4, and the edge 2, 5, these edges are crossing, and the interval 2, 5, and 3, 4 are indeed nested. Okay, so it was first shown by Harberth and Mangerson back in '92 that the complete twisted graph does not contain up to weak isomorphism, this C5 here. There's many ways of seeing this. One way is the following. So for sake of contradiction, suppose in this complete twisted graph, you have 5 vertices such that the 10 edges induced by them, this drawing will be weakly isomorphic to this thing here. The complete convex geometric graph, it has this cycle outside of here. So I guess this 5 cycle. And each red edge on this 5 cycle has the property that it doesn't cross any of the other edges. And so now if I look at this 5 cycle, that means 4 of the edges, these red edges, will be incident to the first and last vertex. But since there's 5 red edges, that means one of the red edges must be within these 3 vertices. So let's say it's F4 and F2, which we know is drawn in this twisted way. But then the edge F3, F5 will cross it. And we know that because the interval F4, F2 and the interval F3, F5 are nested. So therefore, this red edge doesn't have the property that it doesn't cross all of the other edges. And so therefore, we get a contradiction. And so therefore, this thing won't contain C5 inside of there. Okay, so you can avoid C5 in large, complete, simple topological graphs. But what Pak, Shoyimoshi, and Toth proved is that you can't avoid both C5 and T5. So what they showed is that every complete simple topological graph on n vertices contains a topological graph on m vertices, where m is roughly log n to the 1/8. That's weakly isomorphic to Cm or Tm. And so in recent joint work with my students, Ji Zhang, we were able to improve this log n to the 1/8 bound to roughly log n to the 1/4. And I won't give the full proof of this result at the end of the talk or later in the talk, but I will kind of sketch the proof and show some kind of key ingredients on how this bound is obtained. Unfortunately, in the other direction, we weren't able to come up with a non-trivial construction that gets close to this bound. The best known construction that we were aware of is just applying the probabilistic method. So if you just simply take your vertices, let's say on the x-axis, and then for each pair of vertices, you uniformly at random draw a half circle, either above or below the x-axis. And then if you apply the probabilistic method, it's not hard to show that every n-vertex simple topological graph, or there is an n-vertex simple topological graph that does not contain a topological subgraph on basically log n vertices that's weakly isomorphic to Cm or Tm. So unfortunately, we don't know. The gap is between log n and log n to the 1/4. So this result here, at least the original one by Pak, Shoyimoshi, and Toth, it was used a lot in graph drawing. So I guess one corollary you can immediately get from this result here is that once you obtain kind of these nice graphs drawn in the plane, either Cm or Tm, it's not hard to find a non-crossing path, for example. And so therefore, as an immediate corollary of this result, every n-vertex complete simple topological graph will contain a non-crossing path on roughly log n to the 1/4 vertices. However, if you want to find a non-crossing path instead of Cm or Tm, you can do a little bit better. And so we showed that you can get something close to log n. And recently, we were informed that Eichholzer and company also independently proved this bound as well, using slightly different methods. But we actually conjectured something much stronger. So we conjectured that you can find a much larger non-crossing path in a complete simple topological graph. So we conjectured that there's an absolute constant epsilon such that every complete n-vertex simple topological graph contains a non-crossing path on n to the epsilon number of vertices. So polynomial size instead of logarithmic. And the only reason why we made this conjecture is because we know it's true for pairwise disjoint edges, as I mentioned earlier. But whether or not you can kind of connect these pairwise disjoint edges and make a path, unfortunately, we weren't able to prove that. What we thought was even a more basic problem was whether or not in the complete simple topological graph, can you find an edge that crosses very few other edges? So, so if you have the complete n vertex simple topological graph, it's not hard to see that on average, each edge crosses like n squared other edges. But we were hoping to find like a very special edge that crosses very, very few edges.
Andrew,
Uh-huh.
what is the upper bound on the size of a non-crossing path that you can find? Like you conjecture into the psi, but
yeah, I guess nothing. We didn't really think about it, so I guess, you know, n minus 1. So yeah, I don't know anything super non-trivial. Nothing little o n, so constant times n.
interesting. Okay.
Okay. And so if we let h of n be the smallest integer such that every complete n vertex simple topological graph contains an edge that crosses at most h other edges, then it was shown by Valtar that this h sub n is at least n to the 3/2. So in other words, he constructed an n vertex simple topological graph such that every edge crosses at least this many other edges. And then in the other direction, Kinshall and Valtar showed that this is actually little o n squared. So you can always find an edge that crosses at most n squared divided by log n to the 1/4. And actually their proof was based on an asymmetric version of this result here by Pak, Shoimoshi, and Toth. And so if you just follow their arguments line by line and just use our result instead, an asymmetric version of our result, of this result instead, then you can show that h sub n is slightly smaller, but it's still essentially just n squared over polylog n. So we were hoping to significantly improve this. We were hoping to find an edge that crosses very, very few other edges. So we conjectured that it's at most n to the 2 minus epsilon, where epsilon is an absolute constant. But again, unfortunately, we weren't able to prove this. Okay. So now what I wanted to do in the last portion of my talk is to sketch the proof of these two results here. This I'll just kind of start it and show some key ingredients. And then this one I'll also, so they'll just be sketches, but at least hopefully they'll give you an idea of how these arguments go and kind of the tools that they use. So I'll start off with this one where you're trying to find a large CM or a TM in the complete n vertex simple topological graph. So suppose we have this complete simple topological graph on n vertices. We can assume there's a vertex on the unbounded face because if not, you can just project your drawing onto a sphere and then pick a face with a vertex on it, and then project that drawing back to the plane such that that face with the vertex on it becomes the unbounded face. And then your new drawing will be weakly isomorphic to the old one. So we start with a vertex, let's say V0 on the unbounded face, And then we look at all of the edges emanating out of V0. And because of the simple condition, they all have this V0 point in common. And so therefore we have this planar star picture. And so therefore I can order the vertices up here. So let's say I have n plus 1 vertices. I can order them V1 to Vn. No edge will kind of wrap around in this direction because we know that V0 is on the unbounded face. And so we know that basically the edges between these vertices are up here. And so we follow the arguments of Pak, Shui, Moshi, and Toth, where they look at these vertices up here and they look at triples, Vi, Vj, and Vk. And anytime you pick a triple, Vi, Vj, Vk, together with V0, you're going to draw K4. And there's basically only 4 configurations of K4 with these vertices labeled in this simple way. And these are the 4 configurations which they labeled like this. So in particular, this 0, 0, 0 label for this triple Vi, Vj, Vk, this represents the planar drawing of K4. The 0, 1, 0 pattern is where this middle edge emanating out of V0 gets crossed. The 1, 0, 0 pattern is where this left edge emanating out of V0 gets crossed. And then likewise, 0, 0, 1 is the pattern where this right edge emanating out of V0 is getting crossed. So anytime you have a triple Vi, Vj, Vk, you have one of these 4 configurations. And so you give it a coloring. And then what they do is they basically just try to find m vertices such that every triple has the same color. So for example, if you find m vertices such that every triple has this 0, 1, 0 pattern, then it's not hard to see that those m vertices will correspond to the complete convex geometric graph. And likewise, if you have m vertices such that every triple has the 1, 0, 0 pattern, then it's not hard to see that that would correspond to the complete twisted graph. So now we're just looking for a monochromatic clique among these triples. And so just to give you a rough idea of what Pak, Shui, Moshi, and Toth do, so I won't explain it, but I will just mention 2 key ingredients, which is that they apply this argument of Erdős and Rado for 3 uniform hypergraphs to reduce it to a graph. And then they apply the Erdős-Szekeres monotone subsequence theorem. And then they also apply some really nice topological arguments to piece everything together. And this is roughly how they get this log n to the 1/8 bound. And so what we do is we make 2 observations to improve this bound here. The first observation we make is that we notice that 2 of the color classes are transitive, meaning that if I look at any 4 vertices, Vi, Vj, Vk, and Vl, if I know that the first triple, Vi, Vj, Vk, has the 0, 0, 1 pattern, and if I know that Vj, Vk, Vl also has the 0, 0, 1 pattern, then I can conclude that actually every triple among these 4 vertices has the 0, 0, 1 pattern. And the same thing would be true for the 1, 0, 0 pattern. And so because because 0, 0, 1 is transitive, you don't need to find m vertices such that every triple has 0, 0, 1. All you need to do is check that the first triple is 0, 0, 1. And then if you shift over by one vertex, this triple has the 0, 0, 1 pattern. Likewise, this one does too, and et cetera, et cetera. And if that's true, then that's enough to conclude that every triple has the 0, 0, 1 pattern. So it makes it much easier to find a monochromatic clique with respect to 0, 0, 1 or 1, 0, 0. And so it turns out that these two color classes are transitive, and it turns out that these two are not. If you combine them, it's still not transitive, so you have to do something else. Actually, if you just wanted to stop here, if you just wanted to make this transitivity observation, it's not hard to kind of use their old arguments and to improve the bound to log n to the 1/6. But then the second observation that me and Zhang observed is that instead of using this Ramsey argument here, what you can do is use a technique from online Ramsey theory, which is about this Ramsey game between builder versus painter. And so I won't get into it, but in a nutshell, this old argument here, you pigeonhole based on the number of edges and vertices in a complete graph. While here, you only pigeonhole on a subgraph of that complete graph. So the point is that you pigeonhole less in the online Ramsey version. And because you pigeonhole less, you can do better. And this is how we improve the bound further to log n to the 1/4. I thought I was going to maybe present the whole proof of this, but to piece it together and to kind of explain it through slides, it seemed a little kind of tedious. And so I thought I would just stop here by just mentioning these kind of key ingredients. Piecing it together is a little delicate, but it's very doable once you have these ingredients to improve this upper bound here. Okay. So then the last thing I wanted to do is just to sketch this proof here. Sketch the proof that in the complete simple topological graph that you can find a non-crossing path on roughly log n vertices. Whether or not you can improve this to polynomial, I would be very interested in. So it follows kind of the same setup as before, where you pick a vertex on the unbounded face. You look at these vertices up here. And again, you can order these vertices V1 through Vn. And so if we set m to be log squared n, if I look at, so if I start with V1, and if I look at the edges emanating out of V1, starting with this black edge in this, I guess, counterclockwise direction, if I have kind of an increasing sequence of length m, meaning that if I can find m edges emanating out of V1 in this counterclockwise direction, and it goes further, so like this edge goes here, and then this edge goes further, and this edge even goes further, and et cetera, et cetera. And there's m of these edges, then what I get is actually a planar K2M, where these are the two vertices, and then I have the m vertices here. And once you have a planar K2M in a complete simple topological graph, you actually establish a lot of structure in it. Because now if you look at these vertices here, these m vertices, the topological graph induced on them is almost X monotone. So it's actually what's called cylindrical X monotone. Because if you look at any edge between two vertices here, you can't have an edge that goes, I guess in this direction and then comes back over in this direction. Because this blue edge and this black edge here will have 2 points in common, which is at this endpoint and also at this interior point, which is forbidden in the simple drawings. Which means that basically the edges are kind of X monotone with respect to this ordering, or it could wrap around the other way. So it could wrap around the other way, which is like this. And so that's why we called it cylindrical X monotone. And once you have this kind of nice structure, it's not hard to show, and this was observed by Fulick and Ruiz Vargas, that like half the edges, half of these blue edges, so you can find a dense topological subgraph on these M vertices that's weakly isomorphic to an X monotone simple topological graph. So you can find like half of these edges that behave in an X monotone way, or you can redraw it so that it's X monotone and it's weakly isomorphic to the old drawing. And once you have many edges that behave like that are X monotone, then you can apply an old lemma due to Toth, who showed that every dense M vertex simple topological graph with edges drawn as X monotone curves contains a non-crossing path on square root of M vertices. And so therefore, if we're in this situation where we have this planar K2M, because M is log squared N, we would have a non-crossing path on log N vertices. And so therefore, if we have this planar K2M, we would be done. So in the second case, if we don't have a planar K2M, that means when we look at the edges emanating out of V1 in this counterclockwise direction, we should have a decreasing sequence of length N over M. So as I read these edges going from here to here, so this edge goes way out to here, and then this edge goes kind of closer, and then this edge comes even closer, and then this edge here is the endpoint is even closer. So I called it decreasing. So you'll have a decreasing sequence of length N over M by Erdos-Zakaria. And then what we do is we keep the endpoints of those vertices. And then we look at this next vertex and look at this triangle. And either half of the vertices are inside of this triangle or half of them are not. So by pigeonhole, we can assume that, let's say half of them are not, and they're out here. So we throw away, or we divide by 2 times M now. And now we just repeat this process on V2. So either we get the planar K2M or we have this long decreasing thing. And then, since we assume that there's no planar K2M, we can keep assuming we have this decreasing sequence of length, whatever's left divided by 2M. And basically, since we're dividing by log squared N times 2 each time, we can keep doing this roughly log N over log N times. And after we do this log N over log N times, this here, if I look at the consecutive edges, this here will be my non-crossing path. It's not so hard to see why 2 edges would be non-crossing, because since these 2 vertices were consecutive, all of the later vertices will be either inside the triangle or outside. So let's say outside by the algorithm. And so if these 2 edges were crossing, then that means this red edge, since both vertices were outside of the triangle, this red edge will cross exactly one of these 2 black sides here. But then if I look at this triple, the vertex, this vertex, this vertex, as we saw before, there's only one way to draw this K4, since we assume that this red edge crosses this black edge, which would be this configuration here. And here, this is where we get our contradiction, because as you look at these edges emanating out of this vertex in this counterclockwise direction, it's supposed to be decreasing. And here by the algorithm, but here, you know, this edge goes to this vertex, but this edge goes to a farther vertex, which means that it's increasing, which would be a contradiction. And so therefore these edges are disjoints. And so therefore, you know, if you look at the consecutive edges that go along here, you'll have your non-crossing path of length roughly log n. Okay, any questions so far? So this is my kind of last slide or two with the, I guess, usual concluding remarks. We thought it would be really interesting to come up with a better construction than what we did. Whether or not one can come up with a n vertex simple topological graph with no subgraph on little o log n vertices that's weakly isomorphic to CM or TM, just to get kind of closer to this log n to the 1/4. So we thought that this would be quite interesting. And as I mentioned earlier, you know, at least a lot of the theme for a lot of these problems that are open is to decide whether or not it's polynomial or logarithmic. And so the two problems that I mentioned earlier, whether or not you can find a polynomial sized non-crossing path, or whether or not you can get this polynomial improvements on the upper bound on h sub n. So can you find an edge that crosses very, very few other edges? We thought that that these are kind of nice, interesting open problems. It was motivated a lot by the fact that there's a nice connection between these topological graphs and set systems with bounded VC dimension. And in set systems with bounded VC dimension, you have a lot of, you know, short edge lemmas and a lot of, you know, polynomial size matchings and a lot of nice results that give you polynomial bounds. But unfortunately, we weren't able to translate that to, I guess, these topological graphs. And so that's the end of my talk.